So this is a crude prototype of a possible all-mechanical ventilator system. So this is a ventilator clearly of last resort, but it has some key features that I haven't seen in other mechanical approaches to this. The basic parts are the patient end, so this would be mask or ET tube. There's basically a BVM. This in this case is one from Laerdal. This has some unique features that make it really particularly suited for this design. This is actually an inflatable raft pump that's been repurposed for this use. And then there's a connecting rod here and a cam that is driven with a windshield wiper motor. This happens to be one of the more common ones. This is out of a Ford F-150 pickup truck. There's lots and lots of those out there and available. And then a guide system for the connecting rod. There's also some ways I'll talk about how we adjust the tidal volume as well as the IE ratio, which are key parameters. And also the breaths per minute is controlled just by controlling the speed of the motor. So show you there. So this is a readout here. So that's 15 breaths per minute, 20, 25, 30. So it's a slow update rate because the sensor is only seeing the magnet come around every so often with the cam, but that gives you an idea about the controllable range for breaths per minute. So now I'll kind of walk through how the whole mechanism works. So the motor turns the cam. The cam is actually kind of unique. So one of the keys for doing this completely mechanically is to do it with different cams. So these cams would be swappable. The idea is that there'd be 3 of them. The one for an inspiration-expiration ratio of 1:1. There'd be another cam that would be 1:2, and a third cam for 1:3. Could be others as well. And then on each cam, there's actually 3 tracks for the 3 most commonly requested tidal volumes, so 400, 450, and 500 cc's. And so what happens here is that as the cam is rotating, there's a follower down here. This is a bearing essentially that runs on one of those 3 tracks. And the way that is adjusted, I'll show you how it, so here. So in this case, the way we adjust that is by adjusting how deep this follower goes in. So here you can see it running on the 2nd track, and we could, if we put the follower in further, it would run off the deeper track here, which would be the 500 cc. So right now it's running on the 450, and if we run it out shallower, it would run at the 400 cc tidal volume. And the way this works is that this block basically comes off. There's 3 slots on the block that engage the rod in different positions. So for example, if we want to use the 500 cc, which is the deepest track here, we would slide this on here like this. Got to get the head of the screw here aligned. This is and then tighten this down. This basically clamps it directly to the connecting rod, and now this cam follower is now running on the deepest track, which is the 500 cc track. So this is a spring, of course, that keeps the cam follower in contact with the cam, drives the connecting rod, drives the custom piston down here below. And so what I've done here is use this inflatable pump. Really, all I'm using here is the cylinder and the piston seal. So it's a custom piston that takes the standard seal to make it work. So moving further down, there's a 3D printed T here, just essentially a plumbing T. It adapts to the bottom of the piston, is the place where you'd connect your patient plumbing, and also where the ambu bag connects, or in this case, the Laerdal bag. So this is completely stock. This is a standard BVM from Laerdal. Uses all the standard valving, which basically lets you supply oxygen to the patient. This is sort of standard fare. And so this design uses this Laerdal bag completely untouched. The only thing we're doing is basically pumping it, but not pumping it like we've seen with other designs where people are squeezing the bag, which I think is going to have some issues long term with fatigue on the bag. These really aren't made for that kind of use, as well as different bags have different tidal volumes when you squeeze them. So they're different design bags depending on the manufacturer of the bag. So I think each one is going to have to be tuned or set to a specific bag to control the tidal volume. Other than that, it's a standard hookup. So standard medical oxygen comes in here. This is the standard reservoir bag. So all this stuff is exactly familiar to anybody who's familiar with these BVM, these bagging systems. And so the whole system is unique in that everything in here, so the bag, this part, the pump chamber, the hose, all of this is filled with high concentration oxygen all the way out to the patient mask. And so what's unique about the Laerdal system is that they actually move the valving system to the patient end. So where like an ambu bag has the valving down here, the Laerdal system lets you remote and add this tubing. So you have basically zero dead volume, which is really nice. So you don't have to have, or you don't have the patient's exhaled CO2 trapped in the hose. So the CO2 exits directly through the PEEP valve. The only piece that's not shown here, which I haven't been able to find, is the viral filter that would have to go between the exhalation valve and the PEEP valve to control pressure. This is a standard PEEP valve, 0 to 20, and then this guy, this is an adapter, but this is the inhalation and exhalation valve system on this, and so you can see it. We'll put it together. So again, this could be an ET tube or a mask, and now we drive it, and if you see in there, you can basically see the system breathing. So on the compression stroke, so we're pushing air into the patient, you'll see that duckbill valve open, and then there's a pause while the patient exhaled, and that's part of that the IE ratio, inspiration-expiration ratio, which would be determined by the CAM system. So the amount of air that's delivered to the patient is driven by the 3 tracks on the CAM. The inspiration-expiration ratio is driven by the design of the CAM. There's also, with the CAM design, there are dwells for basically maintaining plateau pressure as after the compression stroke, after we've driven air into the patient, oxygen into the patient. You can see the follower will sort of pause for a second to keep pressure into the patient, and then do a quick retract as it basically brings in the next breath into the system, mixing room air with high concentration oxygen, and then delivering that to the patient. So that's it. That's a quick overview of the system. It's crude, but it does work. And the nice thing about this, it's completely mechanical. There is no Arduino, there's no firmware. It's really easy to put together. It's built with a lot of standard parts. These are all 3D printed components. They could be 3D printed, they could be CNC'd. The rest of the parts are all either from the hardware store or McMaster Car or the boat store, not including, of course, the BVM, which would be standard medical equipment. So basically, it's a completely mechanical system designed to be reliable and easy to build, and actually inexpensive as well, which is a nice feature. That's it.